So we're wrapping up series, which means, guess what is probably coming up right around the corner. Actually, I'm probably just going to give it as one a large quiz rather than a full-blown test. And I'm going to save the test for the end of the month. What I like to do, rather than say that the test is given at the end of the unit, is to give you a calendar day and say, we are having a test on this day. Whatever material we get to is what's on it. If we don't get to it, it's not on the test. Okay? This way, you can mark your calendars and know when you have a pile up of things coming at you. Okay? A little bit better for planning. I'm going to look at my calendar, but it'll either be the last day of September or the day before the last day of September, whichever your class period lands on. Okay? So we'll figure that out. And if we run into calendar issues, we'll move it to the first day of October. And I need to be able to see to do this job. All right, so sequences of questions, issues, and concerns. Yeah. Remind me what to. So we have G6 with 1603, and you need to find the and that's all you have? Yeah. I'll just go back to the formulas that tell you what you're looking at. And I'm going to say, I'll just write this one down. Now in this case, n is what? And here. And now you have two equations and two unknowns. And you can either use substitution or you can roll chicken bones, but you have two equations and two unknowns you should be able to solve at this point out. Okay. Also, another thing too, one thing that's always very useful, and I believe it was number 7 where you had, it was like 128 and then 64 and then 32 and then it all ended up at 1 over 512, right? Is one of those problems? Was it 7? Oh, I'm sorry, number 4. The fundamental theorem of arithmetic is very useful. And the fundamental theorem of arithmetic states that if you give me any natural number greater than 1, I can write it down as a product of powers of primes. So basically, I can do a factor tree. And that are two numbers that should stand out to you as being powers of 2. And that kind of lets you know that between the 6th term and the 10th term, I'm multiplying by 2 somewhere. That's 2's engaged in this problem somehow. You don't necessarily need to know right away what it is, but you know that it exists in there. Because 16, 1, 2, 3, 4 is 2 to the 4th, and 256 1, 2, 3, 4, 5, 6, 7, 8. All right. So that's really, really nice to know. You don't need to memorize all those numbers, but being able to do that quick division by 2 is nice. And knowing those numbers and being able to say, hey, that's a power of 2. I got some involvement with 2's in this game, especially with number 4. Because if number 4, you don't have to fool around with logarithms. You don't have to. You can. I was saying earlier that when I did these, there were 2 compound interest problems, right?
Yeah.
Yeah. Those 2 I actually used a calculator for. Because you're dealing with something to like the 20th power some crazy decimal to the 20th power, which is just ridiculous. But everything else I did algebraically. Didn't use a calculator for any of it. We shouldn't have to. Okay. All right. And if you just go to your calculator and you go down a table, you're not really getting what you should be getting out of the problem. The problem is not there as an obstacle for you to jump over. It is there as a training exercise. So I really would like it if you would at least try to do things algebraically. Okay. And on a test, there'll be calculator on, calculator off. Okay. So being able to say, oh, how do I manipulate this thing is important. That's what makes you strong. Okay. Other questions on the homework? This was 2. So I've covered 2, 4, and something else. What else? Yeah. Number 1? All right. Favorite problem. Loved it. Thought it was great. Exactly right. Yeah, I'm sure there are other people in here, but I know I've talked to 3 or 4 people about it. 1. If I give you these numbers, whatever the heck they are, I don't care. Those numbers. And I said, find out, and this is a valid question down here, find out if something is arithmetic, geometric, or neither. If that was the task that I asked you to do, what would you do? Yes. Okay, so I'm going to go ahead and do a division. Woo! Got a number. Is it geometric? So you gotta find the other one, because if you don't get the other one, then we really won't know. So how do we know if these 2 fractions really do prove that it's geometric or not? If they're equal. And what do you do when you have 2 fractions equal to each other? You cross multiply. And you go off to do. And I leave you at that. All right, because at this point you have the tools that you need in order to solve the problem. Okay. And there will be times where I say, here's a series. Oh, sorry, here's a sequence. What is it? Arithmetic, geometric, or what? Or neither. Okay. So you're going to need to know how to attack that. Check. Yeah, there will be times where you will have to fool with that. Absolutely. That is fair game. Other homework questions, issues, concerns? How did this one feel in terms of time? How was time on this one? Okay, show of hands under an hour. Show of hands under 2 hours. As of right now, if you're not finished with it, it's another story. Under 2 hours. Yes? Over 2 hours. That face. You know what? For the record, if you know that now that you know, and I'm sorry that we didn't clarify this earlier, now that you know that you have another day, please don't spend that much time on a homework assignment unless you're really excited about it and you just want to solve it over and over again because it's fun. Then be my guest and go jumping down the lane and carrying your math homework. Woo, Eureka! Yes. So, question. No, the general term is the formula for the sequence. So yeah, find me the explicit form of it. Okay. Yeah, like here's one. And blank. That's the general form for my sequence. Okay. If it was geometric, what the hand was, it was on the other side, right? Things like that. Or we have these formulas, the finite near 1 infinite. 2 arithmetic, 3 geometric, right? The index is the n term. Okay, so like if I'm looking for the 15th term, the index is 15. That's what it means. it will be 0.09 divided by 12. Plus 1. And this is actually what I refer to. I mean, I'm going to take that question and write it a little bit because I wanted to do a little more on interest today, just to show you other problems rather than just a handful. Okay. First of all, why are we doing this here? We're covering sequences in series, and all of a sudden you throw dollar signs at me, wrong code. What's your problem? Why are we doing compounded interest at this time? All right, let's make life really simple. Let's just say we have a loan for $1,000 at 10% interest. Simple math. Okay? All right. Amount final. All right. Now, let's not do this because that's me talking about, for a general term, and I don't want that. My very first amount is $1,000. Now, well, let's not do a loan, because we're going to need to fool with that. It's a little different. Let's fool with an interest-bearing account. Simple as this. Now, and it compounds, and we'll make life really simple. It's simple yearly interest. We'll deal with compounding and all that stuff later. Okay? Simple yearly interest. How much money do I have at year 2? 10% interest. Yeah, what is 10% of 100? That's like 10% of 1,000, right? So what I really have, now this is not really nice because the next month I'm not going to be adding 100, am I? I'm going to be adding some other number. Now, instead, because the bank doesn't say to you, every year we'll give you $100. No, it doesn't say that. It says we'll give you a certain rate. That is that rate, 10%, right? Okay, well now, and this gives me 100. Now, what is that 100? That 100 is not what I have in the bank, is it? What do I have in the bank? I have $1,100, right? I have the original 1,000 plus the 100. That 100 is just the interest. I still have the principal sitting in the bank. So instead of doing this, what I really want to say is this. And I'm writing it in this weird form instead of 1.1 because when I distribute this, I wind up with what I really had just a minute ago. All right, wonderful. Now, 1,100. Okay, third year, what happens? So I have 1,100, and now what do I get? 110. So I'm still getting my original, still getting the principal, and I'm getting my 10%. So now this is 1,100, which is now my new principal, plus I'm getting $110. All right, but now it's getting kind of clumsy. So what we're going to do is we're going to simplify it. Let's say, hey, look, that 1,100 was this, which was this. So now what we can do is we can kind of do a little substitution here. So there's the 1,100. I'm now putting it in front of you. And because all I've done is substitute for that. All right? And now we can see that what we're looking at is that. And if we do it again, A4, we're tacking on this 1 plus 0.1 again. And that's why you're getting that progressive multiplication, which produces a geometric series. Now, the third term required 2 steps, so the nth term requires 1 less. And that's the general form. But this is for my specific case, where I'm dealing with 10% interest over a $1,000 loan. And so if we simplify this a little bit more and go even more abstract, the final amount the compounded piece. The compounded piece, this is simple, all right? Actually, yeah. Because normally you would say step 0 would be your first step. But we can do it. We can leave it as n. Because on the first step, no, it would be -1. Yeah. Depending on how you looked at it, as the beginning of the term or the end of the term. So like, do you get your money at the beginning of the next month or the beginning of the next year or at the end of the first year? Which is formally the part, but actually matters. But this is simple interest. If we wanted compounded interest, what you're basically saying is this. Why does compounded interest look the way it does? Here. It's a year. And I'm going to break this guy up. 12 months. Okay? So, if I invest here and I cash out here, and since we've got more, I'm doing it that way. So let's just say I had, make life simple, 12% interest. Really simple math. So if I put in $1,000 here, at the end of this full year, what I ought to have is 12% more than that. And so now what I would have is this. Okay? But that's if it was compounded once a year, or rather simple interest at the end of the year. You got $1,000 for 364 days, and then on the 365th, boom, we drop $120 in your bank. That's kind of boring, but that's how simple interest would work. But if instead you say, hey, look, man, Mr. Banker, you're using your money. It's not sitting in the bank. It's not sitting there collecting dust. You're using it to give people loans, mortgages, all that other stuff. Okay, when you give money to a bank, it is not sitting idle. It is not just a security thing. It is being reinvested over and over again. So if you have the use of that $1,000 and I don't, I want to be able to pull it right here. I want to cash out right there. Well, I wouldn't get my full $120 because I didn't let you use it for the whole year, right? But I did let you use it for 5 out of the 12 months. So I ought to get a prorated amount. Does that make sense? We all good with that? So what is it? Well, it depends upon how we break up that 12%. If you were compounding monthly, all right, you would get 1% every month. So you would get $10 here, $10 here, $10 here, then so on and so on and so on and so on. And here you would wind up with a grand total of $1,050. And if we had kept going for the whole year, you would have gotten the full 120. So this is why we see the term R divided by N, because you're taking the rate and you're splitting it into how many chunks. Okay? One thing I could say is compounded. Well, if I compounded quarterly, that's every 3 months, so 4 times. So I would get, at the end of this month, I would get $30. Okay, because my rate is 12% all over, well, all over 4 times a year, so that's equal to 0.3. All right, 0.03 decimals, and that times 1,000 gives me this, and I would only get it here. So if I didn't, if I cashed out right there, I would still only have $1,030 because I wouldn't get my next disbursement. Okay, so this is where this guy comes from. All right, and when you do your assignment where it talks to you about compounding semi-annually and then monthly, you come, for those of you who have finished that problem, you don't get the same number, do you? No, you don't. Which one's higher? The monthly is bigger, right? Well, that's happening for 2 reasons. Yeah, sure, as n gets bigger, this fraction gets smaller. But this is not the only time that n pops up. It pops up in the exponent too, all right? And what's happening is that you're doing multiplications. So you're saying, all right, at this point, when I reach here, I'm taking 0.03%, not of $1,000, like I did right here, but of 1,030. And what's that? Somebody crunch that number for me. 103 times, well, 103 times 103. That I should, so 1309. So $1,030.90. No, 1/6. There's, yeah, 1/2, right? So, is that right? 10609? Yeah, that's 1 point, right? Is that good? Now, if we had done it, if you're getting $30 and $30, we wouldn't get this extra 90 cents, which I know is very small. But when we're talking about many years and someone falling asleep in class, there you go. Then that 90 cents actually matters. It adds up quick. Go grab a drink of water. Here. Pass. Sure. Right. Now, this 90 cents is a result of this guy being multiplied out again, okay? So the more times you compound, the better off you are, okay? And that also applies to like things like half-life and other things, okay? Other time, whether you're growing or whether you're shrinking. So that was one of the ones that I wanted to throw at you. Was, if I can find my glasses. All right. Not just interest, but depreciation as well. Where was my example? Endangered species. Erraticus, which is like Chess Online, I'll use that name. It's a great name. Erraticus is an endangered species. Since 1992, there's been one colony removed. Population of the colony was 55. Since then, the population has been steadily decreasing at 4.5% per year. Sometimes you'll see the term per annum, and sometimes you'll see really lazy authors just write so. We want to do the following. Population in the year 2007. Here's what I want to show. See if you can put your brain around it. Because we're going to have to set up our equation a little bit different because of this word. How does that change our equation? Yeah. Bingo. That's it. Because we're not increasing, we're decreasing, which means you're multiplying by a number smaller than 1. And of course, you'll need a calculator for this, would be my guess. And no, we cannot have fractional erraticon. Yes, we can only have fractional rabbits. Well, a partial animal isn't really useful to me. So, unless they're delicious, I want them whole. Okay? Okay, so what happens when you put your erraticon? And so it's requires an amount standard to amount initial. I usually just use these terms, amount initial and amount final. I like them better than principal because we're not always talking about money, right? We could be talking about atoms in a decaying sample or rabbits going crazy in somebody's backyard or whatever. Okay, a virus in a bacteria in a petri dish. And my term is now 1 minus what? And what is it to the power of? 15. Okay. Now, when you crunch this, I'm going to plug in my amount initial, was $550. So this is 555 to 0.955. To the 15th. It's a beast. And I'm going to let the calculator play that game. What do you wind up getting? 278.19 erratici, and so we go to 278 because the 0.19 just didn't make it. Sorry, dude. Yes, yes. Like how? What do you mean? Now, it depends upon how the question is worded. If you say, if it is as specific as saying the beginning of 2007, at the beginning of 1992, it had 555, find out how many were left at the end of 2007, then you're talking about a full year. But if they're an extra year, because you go January to January to January, and then to December. So that's another year, okay? But if you go January to January to January and you stop, then it's just 15, okay? So it kind of depends upon how they played out. And if they did say something like, you know, from January to March, okay, where now we're talking about a fractional year, okay? So my N would now be, you know, 14.3 or 14.25 because we're talking 3 months before, something like that. Okay? Because what we're doing is this is actually really not very accurate because what we're doing is we're assuming that they're dying off in waves. Like every year, a whole bunch of them are walking down the beach and just fall over. But in reality, that's not really happening. What's really happening is that they're being, you know, eaten, or they're not reproducing as often, or, you know, there's maybe a horrible disease or something like that. And in that case, we wouldn't use this formula. What we would do is we would use a continuous one, which would have the E term in it. And we don't need this one for this class. And this is, I think that. N R, number of years. Oh, I'm sorry, not the number of times. Yeah, R. That's where my rate is. You're right. Yeah, this is less math than it is business and finance and whatnot. So, yeah, these things are elusive from time to time. But that's really why we're fooling with all of this. All right, now, one thing I really wanted us to do was talk about sigma notation. Because sigma notation. No, it's really not that bad. All right, and didn't I give you a slide where I showed you what sigma notation was with all those parts? All right, great. There are some properties of sigma notation that I want us to know that are going to make our lives a little bit easier, and then there are some of these that we want to be able to say actually equal a number rather than blow up and go off to infinity when we add a million terms. So properties of sigma notation. All right. C is a constant, 5. Okay. Well, what this is saying is I have C plus C plus C plus C all the way up to N, so it actually stops. How many C's will I have? And as many as I have, as however big N is, right? So this whole thing can be simplified to just C times N. If I have, so simple example again, this sucker is just a list of 25s in a row, right? So 5 plus 5 plus 5 up to 20. And I have 5 and I add it 20 times, I'm going to wind up with 100. Game over. Thank you for playing. Okay? Very straightforward on that one. Stuck to me. We don't need the I in this case because they're all the same in a sense. Like, when I write this, then that's saying the ith constant, which may not be the same as the other constants. So, like, for example, if I had something like this, let capital C right? It's a set of 4 numbers. Okay? Then this guy come back. I want one of you up here. I don't want you. But I do want this is saying the ith element of C, which would be, in this case, 3 plus pi minus 2 plus 1. You see? So, because that's saying I'm doing it, it might change every time, but if it's a constant, then it's always the same. Does that make sense? How about this? I got 16, not including you, sorry. I have 16 students. You are not all the same age, right? So if I added up all of your ages, I would have to go down my roster and say, the first person on the roster's age is 15. The next person on the roster is 16. The next person on my roster is 15. You see, so it might change as I go down my list, you know? But if I said, I have 15 students and they're all 15 years old, or 16 students and all 15 years old, now I know that I have 240 people. 240 years grand total. Does that make sense? If they're all the same. So there is a subtle difference. Okay, can I kill this? Thank you. All right, can I shrink it? What? Oh, just wait until we cover factoring. We'll be ripping little rabbits apart. Fun. Yes, one of the best lectures I do every year. You were there for Broken Rabbits, right? You never saw Broken Rabbits? Oh, just wait. Rabbits are fun. All right. Math can be violent. All right. I have a whole bunch of numbers, and each one of them changes. See? In this case, I is never constant. C was the constant in the other problem. But here, I is the thing I'm actually adding. I'm adding my iterators. I'm adding my indices. Okay? And we've seen this before. What kind of a sequence is this? And what is the general formula for an arithmetic sequence? The sum, not the nth term. S sub n. Gotta know this one. Think of Euler, folding a set. Now, in this case, what's my first term going to be? 1. And what's my last term going to be? If it kept going all the way up to n, whatever it was, it would be. And we usually don't see it written this way. We usually see it written the other way. Let's count on the number, and that's not smart. Know that. Set to it to your eyelids. Know that that summation equals this. Now, which will probably be about October, second week of October. You're going to learn proof function, and you will learn why this is true. So here I'm adding up all my squares. Dang, that was wrong. There we go. And this equals n plus 1 to n minus 1 over 6. Yeah, I believe it's n minus 1. No, it's n minus 1. My fault. We'll see this guy again. These are two that happen so often that they're worth knowing. All right. So, keeping with it. Now, if I have this, let's just use f of x, f of I. I don't like that. Let's just stick with arithmetic terms. Okay. So an example of this might be something like that. You all right? Sure? All right. That might be something where we have a constant, and then we have something going on inside my sigma notation. Well, we can simplify this guy, because every one of them is going to look the same. What do you notice in that expansion when I did all those CAs? What do you see? What do they all have in common? A C. And since they all have a C, I can factor it out as a GCD. And this guy is this guy. So here's the general idea. If I have, I'm just going to clean that up a little bit. So if I have a constant inside my sigma notation, I can pull it out. Okay. And the last one I'm going to give you is this one. And let's actually do an example of this one first. Let's do 5 times. So this guy, and we'll actually do it just to show you what I mean. This is 1 squared plus 1 plus 2 squared plus 2, 3 squared plus 3. I'm running out of space, so I'm only going to make it to 4. It's the beauty of being a math teacher. Squared plus 4. All right, and that's what we have. All right, wonderful. But I don't need the parentheses. I did that just for, visual purposes. So let's drop my parentheses, rearrange what we have. And I'm just going to rearrange right away. All right. That's all of my first terms. And that's all of my second terms. Okay, so I can just regroup, and if I look at my first term, I can write a sigma notation for him. And this guy, I can write a sigma notation for him too. So in general, if I have added things in my sigma notation, I can split it up. Really bad abuse of notation, sigma notation distributes over addition, which is really not really the way it doesn't sound right, but it actually, for all intents and purposes, that's what it looks like. And of course, it does the same thing over subtraction. Not n. Plus or minus, doesn't matter. That's the rule. Yeah. Yeah, it does. Yeah, for sure. It does in every notation. It changes. It starts off at 1 and it keeps climbing up until it reaches n. That's where it starts.
Okay.
That's the first of the indices. Like up here, I is 1. So my first term, I plug in 1.
So this you start at that number?
Yes, and we're going to talk about that. Because really, a good mathematician, a good problem, you should always start at 0 or at 1. If you start at something other than 0 or 1, you can modify your sigma notation to adapt. Okay? And we'll talk about that in just a second, because that opens up the door to a whole lot of really cool problems. Yes? Yeah, I squared minus 1, 2 squared minus 2, 3 squared minus 3, and so on and so forth, which would just mean that all of these second terms were all negative. And then what would happen is all of these guys would be negative, and you could factor out a minus sign. Like that. See that? Okay. Are we cool? Those are the properties that we're going to care about for the most part. All right. Now let's actually see if you were paying attention. Ooh.
I thought they were like to make us understand.
Hmm?
Like, to go over these, like, columns or just to factor them out?
Find the final value of it all. Right. Oh. I was going to give this one for homework, but yeah, Ronco, you suck. Oh wait, not K, I. Sorry. Huh. Well, no, not. You don't need 2 hours. The first term would be 1. So one thing that's useful when you're looking at a problem like this and you're scratching your head and wondering what planet I came from, you go ahead and actually plug it in and see what happens.
Sum equals 4?
Yes, the sum equals 4. So my first term would be, right? Yep, great. My second term would be, and I'm just going to go ahead and do like 3 or 4 or 5 of these and just see what happens. I really, really like this problem. Okay. So let's just see what actually happens here. Well, let's expand this a little bit. What does this first term equal? Thank you. What happens to my second term?
It's the same.
No, it's just 2 times 17. No, third term. And when it's 3x squared over 2 quantity squared, yes, which is 9 squared over 4. But that's not really as wonderful for me, because what are you seeing from term to term to term? What kind of a series is this? Thank you. Shouldn't use x twice. So it is a geometric sequence, infinite or finite. Infinite, we have a formula for an infinite geometric sum. The sum of an infinite geometric series is right? You know what R is. You know what the infinite sum is. You know what the first G1 is. Rock and roll. All right, back together. Yeah, and this is not the only thing that can go sideways. I mean, this is just an example. But when you add different things at each time, then things are, that's neater. Okay.
Like the Lucas numbers and such they were talking about in the video, is there?
Oh, there are all sorts of silly ones that you can make that just go sideways all the time. Yeah, all sorts of crazy stuff. Especially when you throw in weird things, like logs in there, or all sorts of reasons.
They want to have fun.
No, in fact, we have certain rules, and this is where we're going to start off next time. Convergence. Convergence test. Right. That goes to infinity. Here's an example of something that explodes. This explodes. 2 plus 3 plus 4 plus 5, and I go on and on and on. It gets big real fast. Not as big as it could get. It could get really big. Here's another one that blows up. Infinite sums. We're always talking about infinite sums in here. 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3. Guess what? It gets to it. You eventually go to infinity. Right? Well, let's look at these if we were actually looking at them graphically. This guy looks like this. Actually. He looks like a parabola. Because the sum of all of these is actually this. And if you notice that, that's the multiplied out form of the sum of an infinite sum, right? And all this really is just a parabola with a coefficient of 1/2 in front of it, right? So that guy explodes like a parabola. This guy, he, 3 plus 3 plus 3 plus 3 plus 3. Yeah? Just every step add 3. You have a slope of 3, right? All right. So these things, explode out to infinity as they get bigger and bigger and bigger and bigger. In order for my guy to not explode, what has to happen is that my individual terms can't, first of all, they can't stay the same. If my individual terms stay the same, then I have a situation like this. If my terms get bigger, then they explode like that. So what really has to happen is that each term, well, there's only three choices. You either are getting bigger, staying the same, or getting smaller, right? It's the only three situations you can deal with. And since we know that there are infinite sums, there has to be a way for these things to get to exist. So the case where things are getting smaller is what we're fooling with. So, for example, what we really need is this. Each term. Because as I increases, here's so this is a sub I. And this guy, I, S sub I. Sum. Okay, let's think about this for a moment. Each value gets progressively smaller and smaller and smaller, right? What's happening to my sum? It's getting bigger, but each time it gets bigger, it's not getting bigger by the same amount as it was a minute before. The thing I'm adding is smaller this time, right? So the first time I start off with that value, the sum of the first number. And then I add the second number. And then I add the third number. And the fourth number. And the fifth number. And the sixth number. And the seventh number. See what's happening? Is that each time I add a number, the thing I add, that distance versus that distance versus that distance versus that distance versus that distance. You see, each time my addition is adding smaller and smaller and smaller and smaller amounts. You can think about this as a whole bunch of rectangles that are getting infinitely thinner. Does that make sense? Because I'm just adding smaller chunks onto it until finally my sums are so small that I've approached a value and I'm never going to get bigger than it. Kind of like what we did back in Zeno's paradox when I'm standing 10 feet away from the wall. One step, another step, another step, another step, half, 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 half. And eventually I land at 10 feet if I take an infinite number of steps. Same thing is going on in here. So, in fact, there's a term, it's not actually in your curriculum, but it's a really cool little term. This is called Cauchy. That's with a Y, named after the mathematician, Cauchy. And what it's basically saying is that your every term is getting smaller and smaller and smaller and smaller and smaller than the guys behind it. All right? You don't need to worry about this term. But it's the concept of getting thinner and thinner and thinner and thinner, and getting smaller and smaller and smaller additions. Now, we need to be able to prove that we are getting small enough that we will be able to go towards a number. So, for example, let's try this. Well, actually, let's just give it a name. It's called the ratio test. There are many convergence tests. I think there's like well over a dozen, and they're all useful in different times. Okay, we actually were talking about the ratio test a minute before without really even giving it a name. I said that the term in front of me has to be smaller than the term behind me, or me. You know, I can't be getting bigger, because if I'm getting bigger, then I'm in trouble. And if I'm staying the same, I'm in trouble. It has to be getting smaller, right? Okay. Well, the ratio test says that if the absolute value of r to the n plus 1, I shouldn't say r, I should say a, is less than 1, the sequence converges, the series converges. That's the ratio test. It's important enough that you should write it down. All right. In the case where it's equal to 1, it's just inconclusive. You don't know. You're going to have to use a different test. All right. And you will be fooling with things like that, where you'll have to use one test to see if it works. If it's does, wonderful. If it doesn't, use another test until you get a final honest-to-God answer that says, no, it doesn't converge, or yes, it does. All right? There are others, and we'll go into them a little bit further. But, and probably by the middle of fifth, I'll check by the end. All right. You will be given a homework assignment on this. It won't be too bad. It will probably be getting smaller problems, a little bit nastier. And remember, I do want your homework assignment that you thought was due today, next class, and I want it looking pretty, people. Yeah, I don't want a safari.
Wait.
That's pretty. Look, if I have to, like, you know, decipher hieroglyphics, that's wonderful. As long as I don't have to play, you know, mathematical safari, I'll be fine. All right, this episode of the Ronco Show has been brought to you by the ratio test.